Welcome to the course Business Analytics and Data Mining Modeling using R. So, in the previous lecture we were discussing classification trees, and specifically we were doing an exercise in R. So, let us start from the point we left in the previous lecture. So, we were building classification tree model using the promotional offer data set. So, let us redo few points so that we are able to resume from the same point where we left in the previous lecture. So let us reload the data set that we used in the previous lecture for promotional offer. So, this is the data set. Let us import it into the R environment. So, as we saw in the previous lecture, this is a quite large data set, 5000 observation. So, it will take slightly more time. So, we also discussed about the pin code and how we were actually using pin code, how we were grouping different categories of pin codes. So, let us repeat some of those steps so that we are able to reach to the same point. So, pin code, promotional offer, online, all these have to be converted to factor variable as we did in the previous lecture, partitioning, and then we also build the model. We need to load this particular library, rpart library. So, once it is loaded, then we can build the model. We had also saw the tree diagram using a different function, the plot function as well as PRP function. Then we started our exercise about finding the split values or finding the split values for different partitions. So, let us go back to this was where we stopped. So, we were computing the split values. So, this discussion we had already done. So, once for every split variable, the variable that were used to develop the full grown tree, once we have computed the split values, extracted the split values for all the split variables. So, let us so this is the data frame which will give us some useful information. So, the split value that we had computed, now we can see here the same thing which we saw in the full grown tree, and where we could actually follow the root node and what was the split variable and value combination, then the other splits and the predictor and value combination, right. So, the same thing is represented in this tabular format in here, and that is why we required to extract the split value so that we could create this tabular format. You can see node number, the unique node number as we discussed about the tree diagrams, and the split variable that has been used in that particular node number, and the corresponding split value that has been used to create a split, number of cases and the class for that particular node, right. So, so in this fashion we can look at each different nodes that are there. Node number 2, the split variable was spending. So, this is with respect to full grown tree as we saw in the previous lecture. So, this is the split value for spending and the number of cases that are there in that particular node. So, we want to have a look at the full tree diagram again. So, that was quite a big tree model, right. So, this PRP function will give us the tree diagram. So, we need to load this particular library to be able to use this particular function. So once this particular package is installed, we will be able to use rpart this function. So let's reload the library. The name was different, so that was the problem. So it was actually rpart.plot. So PRB function is there, so we have to use this. So now this function would be available to us. So let's plot this. You can see this was quite a big plot tree diagram, and the table that we had generated for split variable and value combination, this is the table that we had generated. Now from here and looking at the tree model, you can get a better sense of what happened in our tree diagram. So you can see first node, root node, income 10 less than 101.5, and that is the node number, and the same value is here you can see in the table as well. Similarly, this is the second node is pending, so the same thing is presented here. You can see the value is also same. So the tree diagram, the information that we have is specifically focusing on the split variable and split value, that we can also present in this tabular format and understand what are the important predictor value combinations. This is especially important if we have quite a big tree, we are developing a full grown tree, and so in those situations this tabular format might be more useful. And you can see the next node number is 4, so the 4 will come here. So this one is the split variable value combination is pending less than 2.16, right, 2.59, so there must be one more. This is the one 4, and then this is the node number 8. So in this fashion you can see. So this is the table for split variable value combination. So let's move forward. So once we have built this model, so let's look at the performance of this model on training partition itself. Since this model has been built, this tree model is a full grown tree. So therefore what we expect is that all the observation would be correctly classified, because once we develop full grown tree, so we keep on creating partitions, we keep on doing splits till we are able to reach, till we are able to create pure homogeneous groups or rectangles or partitions, right. So predict is the function as we have been using in previous techniques as well. So this can be used to score a particular data set. So the mod 1, and we are again trying to score off the training partition itself, and then minus C3. So we are not including the dependent variable outcome variable in this particular data set, and the type is class. So with this we can look at the performance, and you would see that this is the classification matrix. You can see actual value and predicted value. So all the 2251 actual value have been correctly classified as class 0, and you can see 249 actual class 1 records, they have been correctly classified, right. So if you look at we find the classification accuracy and error, you would see it is 100%, right, 1 and 0 here. So you can see the performance is 100% because the tree model is overfitting the data completely. So the whole data, the data set, the training partition has been completely fit with 100% accuracy and 0% error. Now let's look at the performance of this full grown tree model on validation partition and test partition. So we have already created these two partitions. So let's apply the same function predict. Let's look at the classification matrix. Now here you would see few errors, right. 22 class 0 records have been incorrectly classified as class 1, and 12 class 1 records have been incorrectly classified as class 0. So let's look at the accuracy and misclassification error number. So you can see 0.97, so 97.73 percentage, that is the accuracy, and then we have 2.27 percentage, that is the error, right. So so when we apply the model, so there is this much difference in the performance of the model. So it is, of course, this is expected, because it is not possible for the overfitted 100% overfitted model to perform well on new data. However, the 97, this performance is also quite good. However, this is expected that it would be lower than the training partition. Now let's look at the test partition and the performance. Now let's look at the accuracy and misclassification error numbers. So you can see 97.4 in this case. So if we compare from the previous performance, so you would see then that in the validation partition it is 97.7, and here it is it has decreased 97.4. So if we compare from the training to validation and test, so 100 to 97.7 to 97.4. So the performance is, though the performance is good for all the partition, but it is decreasing. If we are interested in looking at the information the way our output is presented, so we can use the summary function as we have been doing for other techniques as well. We can look at the details here. So this is quite big output, reason being that there are too many node numbers, because this is full grown tree. So you can see in the summary output the call of this particular function, the details, the number of observations. Then this is the CP table. The CP table, this is complexity parameter values. We will discuss this particular, what these values are about in detail later on. N split is the number of splits, and then the relative error. So we will discuss all these three terms later on. Now let's look at the variable importance. So for if we compare this to the previous data set that we had used, the Siddharnagar data set, we had just two variables, right. So now in this case we have quite a few variable here, and so you can look at the variable importance. Income comes out to be the most important variable, 44% importance, then followed by education, and then followed by family size, then followed by spending, then pin code and age. So from this we can also understand. So this, as we talked about, that classification and regression tree can also work as a variable selection approach or dimension reduction approach. So from here you can see that we can have a rank ordering, a list of the variables which are more important, and so from that list again we can based on our domain knowledge and expertise and looking at these numbers, we can again understand which variables are important, so which variables to retain in the model. Now if we look at the splits, the partitions that are how they are being created. So node number 1, we can look at this. So some specific details, complexity parameter value, and other details we can clearly see here, predicted class, expected loss, and all those. Expected loss is nothing but the node root node, it is classified as class 0. Right, because majority of the members belong to that class 0. So what would be the loss? That is proportion of records which belong to the class 1 which would be incorrectly classified. So that is the loss here in this case. Node probability of this node probability is 1, because this being the root node. So the class counts are also there, the probabilities that is also there, as you can see here. You can see left sun 1926 observation will go to the left sun, the right sun the remaining 574 observations. So the same thing you can visualize in the tree diagram itself, right. So here, however, the node details, this is not given here because of the space problem in the tree diagram. Now, the primary split, the split that has been performed is income less than 101.5, which we can see in the tree diagram as well, the same information. Now, the improvement value that you can also see here after the split is performed. So, this is the improvement that is expected if this is the split that is done, right. Similarly, if for node number 2 we can look at other details, 1926 observations and the complexity parameter value and then other details as we saw in the root node. Now, look at the split spending less than 2.86, right, improvement 3.31. So, node number 2. So, this is the node number 2. So, if the split is performed in this fashion using this predictor value combination, we can look at the improvement and other things. So, similarly, for all the node numbers in the summary output, for all the node numbers, this detail we can find out, right. For all the node numbers, this detail is available. So, further importance of some of these numbers that we have been talking about, for example, complexity parameter and other things, as we said, we will discuss in the during the lecture itself. Now, now that brings us to our next part, that is pruning. So, let us go back to the slides. So, as we have talked about, we have discussed in the in some of the starting lectures of classification and regression trees that there are two primary steps in CART procedures in CART algorithm. First one is recursive partitioning, the second one is pruning. So, till now our discussion has revolved around the recursive partitioning, where we try to create the full grown tree. We have tried to achieve pure homogeneous subgroups, right. Now, as we saw that this particular, once we develop full grown tree, it overfits the whole data. And so, how do we avoid this? So, pruning is the next step that can help us in avoiding overfitting. So, the idea is to avoid overfitting. Why we perform pruning? The idea is to avoid overfitting. So, full grown tree leads to complete overfitting of data, as we have been saying, poor performance on new data. So, because of the overfitting on new observation, the performance will further decrease. Now, if we look at the way tree models or in general other models that we have been talking about, the focus is on typically the focus is on overall error. So, we always look to minimize overall error of classification models and also for tree models as well. So, what happens in when we try to minimize overall error? So, this particular error for any particular technique and also for tree models, so this is expected to decrease until the point where relationships between outcome variables and predictors are fitted. So, till the time the relationship between outcome variable and the set of predictors that is being captured, that is being tapped in by the model. So, the till that time the overall error will continue to decrease, right, as we keep on building our model using that relationship, using the information that is there in those predictors. So, till the point the predictors information is being used to build the model, the overall error will decrease. However, there is going to be one point where all that predictor information that could have been captured, that could be captured depending on the different strengths and weaknesses of different techniques, and for tree models as well. At some point the models will start fitting to the noise. Once the all the predictors information that could be useful for that classification task or prediction task in general, once that has been done, the model will start fitting to the noise and overall error will start increasing. Once we start fitting to the noise, the overall error will start increasing. Now, why specifically we talk about the tree models, why that would happen, and in general also due to as you can see in the slide as well, due to splits involving a small number of observations. So, as we keep on doing splits using predictor value combinations, so initially for every split will get much more reduction in overall error, but as we go along and most of the predictors information has been built into the model, and once we start fitting to the noise, we will also reach to the point where we are actually dealing with a small number of observations. So, we are further creating more and more splits. Most of the observations have already been put into their right rectangles, right partitions. Now, further we are looking for few observations which are still to be correctly classified. So, because those observations, as we did through an exercise using a Sedan-cast data set, the partition that we kept on creating using the graphic, right. So, finally we were also changing even if there is one point that is incorrectly classified in a particular group, we also created a partition for even that one single point in that exercise, right. So, you would see that essentially we are dealing with a small number of observations as we do as we do too many splits, right. So, because of this, the tree models in general, other models also, they start fitting to the noise after some point once the predictor information has been modeled. So, the overall error will start to increase and will start fitting to the noise. So, the same thing happens in the when we develop full grown tree. We keep on splitting, we keep on creating partition till we reach to the till we generate pure homogeneous groups. So, some of the last splits, some of the last split which have been created based on few observations. So, they are leading to they are actually fitting to the noise. So, how do we overcome this? How do we overcome this complete overfitting of the data? So, there are two approaches. So, one is stop tree growth before it starts overfitting data or fitting noise, right. So, we have to find out that point where the tree has stopped building the predictor, stop using the predictors information to build the model, rather it has started the model has the technique has started overfitting the data or noise. So, how that can be done? So, number of splits or tree depth level. So, if we can find out that optimum number of splits or tree depth level where this actually can happen, where this is actually going to happen, the overfitting of data or fitting to the noise, the number of split after which this starts to happen. If we are able to find out that number, then probably we can stop tree growth there and will get the optimized tree. Second approach could be number of observations in a node to attempt the split. So, how many observations could be there before a split is attempted. So, if we are able to understand for a particular problem in the data set, keeping everything in mind, if we are able to determine that, then also we can stop tree growth. Accepted level of reduction in impurity. So, once we create a split, we are expecting certain reduction in the impurity, different two important impurity matrix we talked about, Gini index and entropy measure. So, what is the level of reduction that we expect once we create this split, once we create partition and different subgroups. So, if we are able to determine a accepted level of impurity, reduction in impurity, so that can also be used to stop tree growth. So, this is another approach. Now, these three things that we talked about, whether it is the number of splits that can be performed, optimized number of splits, or optimal number of observation in a node to attempt the split, or the accepted level of reduction in impurity. If so, you would see with all these three approaches, it's difficult to determine these points. And how do we determine the number of splits or number of observations? It's slightly difficult. More number of experimentations would have to be performed, right? It is going to take a lot of time to build the model and to find the optimum these points and optimum values of some of these approaches. So, because of this difficulty, this particular approach is not that popular, and there is another approach that is generally tried, which is actually the pruning approach. That is the focus of this discussion, this particular exercise also. So, prune, the second approach is prune the full grown tree back to a level where it does not overfit or fit noise. So, that is the second approach. So, once first we can develop the full grown tree, and then we start pruning it back to the level where it does not overfit data or fit noise. So, that is one approach. How it can be performed? We can use validation partition. So, we can build our tree, we can construct our tree using the training partition, and then we can start pruning it back using the validation partition. So, this is one particular technique. So, we talked about in the starting lectures of this course, we talked about the importance of partitioning, the training partition, the validation partition, and also the test partition. Where but if we look at some of the techniques that we have tried, we have just been creating two partitions, training partition and test partition. Now, in this particular technique, you would see the importance of validation partition. Training partition is being used to build the tree, that is full grown tree. Validation partition is being used to refine the model, to fine tune the model. How? To prune back the tree to the level where it stops fitting to the noise or stops overfitting to the data. So, validation partition also is going to be in a way part of the modeling process, and therefore, the importance of test partition, which would act as a new data partition, and where we can apply our model and check its performance. So, in this particular technique, we see that the training partition and the validation partition, they both become part of the modeling process. So, in this approach, the pruning approach that we just discussed, the idea is to remove the tree branches. When we talk about removing the pruning the tree back to a certain level, so the idea is to remove the tree branches which do not reduce the error rate further, right. So, if the error rate is not some of the branches which are not able to decrease the error, the overall error, then probably we should remove those branches. So, that is the main idea. So, to implement this particular approaches, we need to be able to identify or determine the branches or the nodes which are not decreasing the overall error further, and then remove them off, snip them off. So, with this, so a few other things in pruning. So, as we talked about, find the point where error rate on validation partition starts to increase. So, we talked about the point where construct the full grown tree and use the using the training partition, and the prune it back using the validation partition. So, first we need to find out the point where error rate on validation. So, we can build the model using training partition and then apply, then score the validation partition and check the error rate and find out at which point the error rate starts to increase. That is the point, that is the level at which till which we have to prune the tree. So, another concept related to this pruning is cost complexity parameter or complexity parameter CP, that is generally used in CART algorithm. So, the complexity parameter values are typically used to perform the pruning in many implementations of CART. So, what is complexity parameter? So, if you look at the definition here, this complexity parameter, that is CP, is error, that is nothing but the overall error that we talking about, the misclassification error. So, CP is error plus PF into TL. PF is the penalty factor and TL is the tree length or tree size. So, for tree size we introduce a penalty factor and error plus this penalty factor. So, that will give us the CP value. So, if there are two particular tree models, two candidate tree models, and they both have the same misclassification error, but if a particular they have both these tree models have different tree sizes, different number of nodes. So, it is the smaller tree model that would be selected, that would be based on the complexity parameter, because there is going to be penalty on this on tree size. So the model having bigger tree length or high bigger tree size would have additional additional value on added to this error component, and therefore its error, the CP value would be more than the tree having same misclassification error but of a smaller size. So complexity parameter or cost complexity parameter in a sense can be used to control the size of the tree, to control the length of the tree. So a complexity parameter can also be used to prune back the tree, and as we have talked about that validation partition, that can be also used, error rate, and we can also identify from where it starts to increase. Or the second approach is compute the complexity values and complexity parameter values and use that to find out the optimum length of the tree. Now we'll stop at this point and we'll continue our discussion on pruning in the next lecture. Thank you.